Hello AP Statistics students. In this video, we are going to take a look at something probably brand new to everybody, the z-score. It's a standardized score. All right, so our objective here is we are going to calculate and interpret the z-scores of individuals in a distribution. We will use these z-scores to compare individuals in different types of data. Okay, so hopefully you're thinking, Bolt, what the heck is a z-score? So a z-score, what is it? All right, it is a way of measuring how far a value is from the mean, from essentially the center. Okay, now if we're going to be measuring something, what are we measuring with or in? Are we measuring in feet, inches, miles, seconds? That's the confusing thing about a z-score. Our unit of measure is the standard deviation. All right, so imagine we have this ruler and we want to know how far away from the mean is a piece of data. So we take our measuring stick, and what are these little tick marks on our ruler? They're not inches, they're not feet, they are standard deviations. Okay, that's what we use to measure how far from the mean we are. Okay, I guess my bad, that was no good. How far from the mean we are. All right, how do you calculate it? This is a very simple calculation. All right, a z-score is equal to, you take your value and you subtract the mean, and then you divide by the standard deviation. That's it. If you want to see it in symbols, here's what it is. Z is equal to x minus x bar over s sub x. All right? Very easy. I think about those poor freshmen right now who are having to do the quadratic formula. Man, this is super easy compared to the quadratic formula. How do you interpret this then? Like, what's the sentence you're gonna have to write? All right, you're gonna have to write a sentence, blank. All right, that is your context. Is blank standard deviations. Okay, and that blank right there is your z-score. Above or below the mean. All right, how far above or below? All right, and that is measured in standard deviations, either above or below the mean. All right, hopefully I haven't lost you yet, because this is actually quite easy, and it is one of the most important things we do all year. So let's return to the data from Mr. Tabor's first stats test. We have the dot plot along with the summary statistics. So we've got the sample size, 25 people, the mean, 35, the standard deviation, and all of our box plot numbers, min, Q1, median, Q3, and max. Nice summary there. So find and interpret the z-score for, oh, poor Jacob, who earned an 18 on the test. So our z-score is equal to 18, the value, that's Jacob's score, minus the average, divided by 8.77, the standard deviation. And that gives you negative 1.99. So that means, here's my context, Jacob's test score is 1.99, that's the z-score, standard deviations below. Now, how do we know it's below? Because it was negative. Okay, that means we are to the left of the mean. We are under the mean, below the class mean of 35.44. All right, so hopefully that makes sense. If their test score is above average, then the numerator is going to be positive. If their test score is below the average, then this subtraction problem will be a negative result, and then your whole fraction is negative. All right, now you got to also do that backwards. Tamika had a standardized score of 0.292. She was 0.292 standard deviations above, this time, the mean. What was her test score? We use the same formula, only now we know what z is. So this number right here is right here, 0.292. But we don't know the test score, so you can think of that as your solve for x. Woot woot, yay, algebra. All right, that was enough. The mean and the standard deviation stay the same. How do you solve this equation? Multiply by 8.77 to both sides. That goes away. That gives you this step right here. Add 35 to both sides, and you get the answer of 38 was her score. So again, this is like the algebra problem. If we give you x, you find y. If we give you y, you find x, kind of thing. You've got to be able to go both directions. All right. Students in an AP Stats class measured all their heights. Here is a dot plot of their data along with summary statistics of the data. All right, so we got our heights, summary statistics along with our sample size, our average, and our standard deviations. Let's do these calculations ourselves. So Lynette is in this class and is 64 inches tall. Find and interpret her z-score. So the z-score is equal to her value, which is 64, minus the average, which is 67, divided by the standard deviation, which is 4.29. So when you type this into your calculator, be careful with order of operations. 64 minus 67, hit enter. All right, so it's -3 on top, divided by 4.29. I usually always do that in 2 steps on the calculator. You don't have to write all the steps. -0.699. If you wanted to round that up to -0.7, that is probably just fine. So what does this mean? There we go. So Lynette's test score, what am I saying? Lynette's height of 64 inches, there's my context, is 0.7, my z-score, standard deviations below the mean of, well, is our average 67 inches tall. Okay, there is our context and our interpretation of what that z-score of -0.7 means. All right, now we're going to go backwards. Gerald's height is 1.165 standard deviations above the mean of this class. What is Gerald's height? All right, so when you see this whole first sentence, 1.16 standard deviations above the mean, you do have to now think z-score. Okay, so that's going to go into my formula. 1.165 is equal to the value. I don't know the value, so I'm going to put an x, minus the mean, which is 67, divided by 4.29. So I just got to do this algebra now. Hopefully that's not too bad. Multiply both sides by 4.29. That goes away. We're left with x minus 67 is equal to 4.29 times 1.165. 4.997. And then we're going to add 67 to both sides. Our value is, plus 67, oh my goodness, 67 plus, let's call that 5, is going to be 72. All right, let's just round this up to a 5 and call it good. So he is 72 inches tall. Now you might be thinking, all right, that's nifty and everything, but what good is that? So the power of standardized scores, or z-scores, is that you can now compare two things that are very, very different. So, two student athletes are arguing about who performed better at a recent track meet. The problem is, one of them is a long jumper and the other is a pole vaulter. How can we compare these two athletes if they don't even jump in the same direction? Statistics to the rescue, yay, math is cool. All right, we will compare the long jumper to all other long jumpers using a z-score, and compare the pole vaulter to all the other pole vaulters, and see who was the farthest away from their own average. Okay, so they each get their own ruler, essentially, against their own competitors. So, our long jumper, let's say they jumped 18 feet, and our pole vaulter jumped 15.5 feet in the air. And then we had to look at all the other long jumpers. So let's say they had an average jump of 16 feet with a standard deviation of 0.8 feet. And then here are the statistics for the pole vaulters. So what we do is we compare the z-scores of these. So I'm going to find our z-score for our long jumper. So they're 18 feet minus the average of 16 feet divided by 0.8. And our pole vaulter's z-score, which will be 15.5 minus 13 divided by 1.1. So we do both of these quick setups. 18 minus 16, oops, why is that not 18 minus 16 divided by 0.8. So this has a z-score of 2.5. So this person was 2.5 standard deviations above their mean. All right, this person now, 15.5 minus 13 divided by 1.1. This one is 2.27. All right, so the z-score sort of gives you an idea of how remarkable their score was, because it's how far above the average they are. This person was 2.5 standard deviations above their mean. But this person was 2.27, not quite as far above their mean as the long jumper. So in this case, the long jumper, this jump of 18 feet, when this is what people can do, is a bit more extraordinary than this pole vaulter score, or jump. And so the z-score really gives us an idea of how extraordinary a piece of data is. If it's really close to the average, well, everybody's close to the average. But as you get farther and farther away from the average, it becomes more and more extraordinary. So here we got to tip our hat to the long jumper. That is a bit more extraordinary than the pole vaulter's jump of 15.5. All right, there is our first intro into standardized z-scores.